Hello and welcome to part 2 of the wavetable oscillator. Today we will tackle the issue of anti-aliasing our wavetable for richer waveforms like square waves, triangle waves, and sawtooth waves. We'll start where we left off in the last tutorial. I'll leave a link in the description for this. Let's go ahead and play that and see what we have. So just a simple sine wave with frequency controlling the x-axis. Alright, so let's convert that sine wave into a square wave. There's a couple ways we could do this. The way we'll approach this today will be to do additive synthesis. So here we have in our setup loop, we are going through our entire buffer that we're storing this in, and we're making one sine wave with this function here. Okay, so what we need to do is make another loop. Every sample of our buffer will need to add one sample per harmonic. So if we go for, and we can't use I again, so we'll use j equals 0, j less than number of harmonics, which we don't have yet, and then increment j. We'll move this logic in here, make a number of harmonics. Let's do 50 harmonics. Alright, so for each sample of our buffer, we'll add 50 harmonics. Alright, so a square wave has integer multiples of the fundamental frequency, but only odd integer multiples. So, let's see. What we can do is j equals 1. And j equals the number of harmonics. That way we start on number 1. Let's change this to I times 2 pi divided by table size. Alright, and we'll cast this as a float. Alright, so this should be now j times 2 pi. Sorry. I, and then times j. So this is essentially our frequency. And then we can take our frequency times our integer j. So times j. And then we need to do every other harmonic. So if we start this at 1, this will be this, it'll add the first sine wave that we had. This will be no different than it used to be. But instead of incrementing by 1 each time, this is like saying j equals j plus 1. We can do j equals j plus 2. So this will go 1, then 3, then 5, then 7, etc. All through all 50. So we'll add all harmonics there. So instead of setting this equal to, we'll have to say plus equals. So our wavetable at I will equal our wavetable at I plus the sine theta of our new harmonic. And if we're using plus equals here, we'll have to set it to 0 to begin with. Because otherwise it would have been null, and adding something to null doesn't make a lot of sense. Okay, so now we should get 50 harmonics. I'm going to put this in parentheses for a little more clarity. And we are drawing the waveform, and we are listening to the waveform. So we will be able to see and hear what this is. All right. One thing I did neglect to do is to taper off those high harmonics. So that wasn't correct yet. What we need to do now is to, let's see, table size times j. So this will taper off the harmonic. All right, we can make this a little more clear. I'm going to put that back, but this will be the same thing as saying. Actually, let's put it here. Okay. times 1 divided by j. So since j will start at 1, we don't have to worry about a divide by 0. But this will, let's do a float. So each time we add a harmonic, it will be this much quieter. It'll be 1/3 the amplitude, then 1/5 the amplitude, then 1/7 the amplitude, etc. And this will give us our square wave with 50 harmonics. Alright, and the whole point of this tutorial is going to be to show how to get rid of aliasing. So aliasing sounds like this. Here are a lot of absurd artifacts up here. Okay, so if we add even more harmonics, which 1,000 isn't unheard of. Let's do 500 first. Alright, so you can see the waveform is a little tighter here than it used to be, but we start aliasing a lot sooner. Okay, so we need to be able to use a wavetable synth for a square wave or a triangle or a sawtooth wave, but not have it alias. So a solution for this is having a wavetable per octave. All right, so one thing we'll need to do, let's go to our header. We're going to have to rethink this whole thing. So right now our wavetable is pointing to a float, which is an array. Let's do what's called a two-dimensional array. So a float wave table. This will be number of tables. And then table size. All right, so this is new. Let's actually define the number of tables up here. All right, so this format, float name, : this is an array of arrays. There's a couple of different ways to think about it, but right now the simplest will be, this will be which table we're referencing, or which octave in our case, and this will be where are we in that waveform. All right, so it's a little tricky to gather. You can find some information about two-dimensional arrays in C++ on some forums. Let's go back to the CPP. We'll have some errors here since our wavetable needs 2 values. Okay, so let's redo all of this. So we're going to need to fill each one of those 10 tables, or 10 arrays of tables. So we're going to need a loop for int I equals 0. I is less than our number of tables, so 0 to 9 here. Increment I. All right, so this I is going to be our table. And then we're going to have to fill, for each of those tables, every value. So for int j equals 0, or table size, j++. All right, so now we have our nested for loop. This will go through every single sample of every table. So at the end of this, we'll need to add wavetable at I, which table, which sample in that table. All right, so we'll start with table 0. We'll go through every sample of table 0 and enter that. Then we'll increment to table 1, which is the second table. And then we'll go through every sample of that table, etc., until we've gone through every one. And as I said before, these are not going to be valid any longer. Let's go ahead and get rid of some things we don't need. We will still need some way to keep track of the number of harmonics, and we'll go through the logic of getting these frequencies again. However, we do need to know how many harmonics are appropriate for each part of that table. And this is where it gets a little tricky. So we need to determine our Nyquist frequency, which I'm just going to make that a hard frequency. I'm going to say our Nyquist equals 20,000. 20,000 hertz is vaguely the highest frequency of human hearing. Our Nyquist frequency is technically 24,000, but there's no point storing samples we won't be able to hear, and this gives us a little headroom. So even if somebody's using a higher sample rate, I'm still going to keep this at 20,000, just hard code that. All right, so what I want to do is collect the lowest frequency for each table. So that's going to be, I'll make that an array. And this will be a 10 large array. This array will hold 10 values. So let's add that here. Float lowest freq list. So a list of our lowest frequencies. Back to our CPP file. All right, lowest equals new float. We'll do 10. Num tables. All right. No. All right, so we'll set each one. So for int I equals 0, I is less than 10. Increment I. All right, so I have found a way to do this. Let's make a value called current low, and I'm going to set that equal to 20. I'm going to assume that 20 hertz is the lowest frequency that will be available to a user who uses this library or who uses this wavetable oscillator, which is reasonable because 20 hertz is considered the lowest frequency we can hear. So if somebody wants to listen to an oscillator, it's reasonable to constrain the frequency from 20 hertz to 20,000 hertz. All right, so our lowest frequency list at I equals our current low. And then since we're doing one table per octave, we just take 20 up an octave, or current low up an octave. That's simple in this case. We can just take that times 2. Current low equals current low times 2. All right, so next time it comes around, it'll be 40, and then the next time it comes around, it'll be 80. The next time it comes around, it'll be 160, etc. All right, so now we have the list of our lowest values. So we need to make a number of harmonics per octave. And we don't, at the moment, we're going to assume that we could calculate this in advance and store this and never change anything. But let's make this flexible. So we'll have, I don't think we've used it in the series, but a while loop while we still have harmonics left. So we have to figure out how to surmise that. So while 20 times num harmonics is less than our Nyquist. Add more harmonics. All right, so our Nyquist is set to 20,000. Let's, this won't be valid anymore. We can't hard set the number of harmonics. That would be dependent on the octave. So every time we do this, before we go into here, we'll know we'll have at least one harmonic. So float num harmonics equals 1. All right, so 20 times 1 is less than our Nyquist. So we'll go ahead and add that to our wavetable. So our wavetable at I, j equals, we'll set that to 0 for now, which will not be true, obviously. All right, so one thing we need to fix is that this is hard set to 20. This needs to be changing every octave. So this will be right for our first octave, or our first table. We need to make this our lowest freq list at I, which will be going from 0 to 9, going through our tables. All right, so now this will start at the correct octave each time. So it'll start at 20, and then it'll check all the harmonics, and it'll stop this loop whenever it gets to the Nyquist. Okay, so let's get back to the logic. So to make a sine wave at this frequency, we needed to know let's see here. I think I need to do some stuff out here again. So our table fundamental frequency, fundamental freq, we can put this back, it's still valid. That is equal, unless we still have it down here. Yes, we do. I'm going to move this up from the last tutorial. So here we'll have j times 2 pi times num harmonics, since this will equal the current number of harmonics. So each time we go through this while loop, we'll add one more harmonic. And since we're doing a square wave, we'll need to do plus equals 2, or number harmonics equals number harmonics plus equal 2, since we are skipping every other harmonic. So this will start on 1, go to 3, then 5, then 7, etc. Just like I did before, it's just in a slightly different format now. And this will be divided by our table size. All right, I'm going to put this in the parentheses to keep it clear. And it's unhappy, and I'm not sure why at the moment. We'll see. Okay, it's happy again. All right, and as we did before, oh, this is not correct yet. Sorry, this will be theta. All right, and then we can do wavetable is equal to the sine of theta. And then we'll scale it by our amplitude. And since this is a square wave we're making, we're going to multiply this by 1 divided by j. Or sorry, number of harmonics. Or a harmonic number in this case. All right, so if we're on the 4th harmonic, this will be odd, so 1, 3, 5, 7. This will be 1 divided by 7, and we'll scale this output appropriately. All right, and we need another parentheses here. And I think we are good to go here. Why is it unhappy here? Ah, I don't have an equal sign. All right, so there's a lot to take in here. So we had to make a way to populate every octave algorithmically. So that's what we've done here. So now we have a 2D array stored in RAM. We will need a way to keep track of what octave we are on. So to do that, we will need to linearly interpolate between the octave we're in between. So basically, we'll be crossfading between one harmonic and another. Let's make a function to make a current octave. We'll fix these issues here in a moment. So let's go to our header. And we need a function to take the current frequency and give us back which octave we are on. And this will be a floating point since we actually are going to be between two of these wavetables. So we'll need a function here. Get octave location. And then we'll need to feed this function frequency. So we'll give this function our current frequency. We'll get our current octave location, which will be anywhere from 0, 4.5, up all the way up to 9. and no higher than 9, no lower than 0. All right, so now we have this function. Let's go ahead and copy that, go back to our CPP. We can add this right after the audio out. Float of app, get octave location, float frequency. All right, let's keep this tidy. All right, so we can do a couple things here. We know we'll have to return some number. So if freq is greater than 20,000, greater than our, what do we call this, our lowest frequency list. This is why it was handy to keep these in an array. Our lowest frequency list at 9, our highest point in there. Return 9. All right, and let's keep a variable called our current octave if we don't have it at the moment. Float current octave. Current octave equals 9. All right. So now we can make a function to, let's make an integer called index and another while loop. So while, let's see, what's the best way to do this? So while the frequency that we give this function is greater than index, or sorry, our lowest freq list at our index, continue to move. All right, so this will go through, and then at the end we'll have to increment our index plus plus. So we'll check the next one to find out which octave we are in. So we'll start at 0. So our frequency is greater than our lowest frequency list at index 0. We should increment. There's one of two things can happen. Either we're in the right spot, we're in between the right two octaves, or we're not. So let's find out if we're in the right spot. If our frequency is less than our lowest freq list at index plus 1. So if the next index is too high, but the previous index is too low, we know we're in between the right octaves. So if we're in between the right octaves, we'll have to return the position between, which we'll get back to in a moment. However, if we're not between those two octaves, then we'll need to increment the index. And then try again. Since we're in a while loop, this will go until this is true. So eventually, our frequency will pass this test. If we return, which we will eventually, then this will stop the while loop, and it will stop this function, and it will go on no longer. All right. So to find our position, we'll need to return I plus how far we are between that octave. Unfortunately, the octaves work exponentially. That's why every time we added the next octave, we took the previous result times 2. So that's an exponential relationship. An easy thing to do, since we're using octaves, however, for our tables, is to take the next, or our location, which is frequency, or sorry, just freq, our input to this function. And we can divide that by the the next lowest. So how far are we away from the previous frequency? So this will be lowest freq list at index. All right, so this will always return, since we're in octaves, either 1 to 2. it'll be twice the size as at the maximum, or be less than that size. So we need to do lowest frequency. Just put this in parentheses, and then subtract 1. So now this parenthesis set will return anywhere from 0 to 1 as a floating point. And then our base index, which to say this is 3, this will be 3.4, adding this with it. All right, so I think this definitely accounts for if it's above the highest index, and immediately leaves the equation, leaves this function if not. If it's not above the highest index, it's going to start at 0. And if our frequency is greater than 0, yeah, we actually should not enter this while loop if our frequency is less than our lowest index. So let's go ahead and check that. So if our freq is less than or equal to lowest freq list at 0, current octave equals 0. So we'll just have to use the lowest table we have. All right, so I think this is safe once we figure out what the issue here is. Oh, I call this index, not I. Okay, so what we have now is a way to hand this function a frequency and get back which of those 10 tables we are. And not only which table, but how far we are between them, so we can crossfade between the appropriate tables. We'll leave the crossfading to a little later. Let's go ahead and get this to work, and so we can see everything that's happening. So we're going to update this table every time. So this should be wavetable at our current octave. And then this should be I. So this will draw the waveform that we are currently using. And let's see, so linear interp from wave current octave. And we'll have to make this an integer for the moment. All right, so this function is getting rather long, but it should still work. And we'll have to set our current octave somewhere. So current octave equals get octave location. And then we'll give it our current frequency. All right. So this will be a small miracle if this works after all of those changes, but let's go ahead and try. All right, we can see very clearly that we are adding harmonics. So there's something wrong with my algorithm of how we made those. There's clearly a sine wave. All right, so let's investigate why this is wrong. It appears to me that the actual wavetables themselves are wrong, but our moving between them seems to work out fine. So let's go, and that's why it's good to visualize since we have the ability to do so. So our number of harmonics is equal to 1 at first. So while the lowest frequency times number of harmonics will be 20, then 60. Anyway, while it's less than Nyquist, we'll add a harmonic. So for our harmonics, we have theta equal to J. So this is our phase. J is our phase here. j times 2 pi, and then our phase will go faster if we're at a higher harmonic, and that will be divided by our table size. So that's correct. So this will be 0 to 2 pi if it's the first harmonic, 0 to 6 pi if it's our next harmonic, which that's right. So interesting. Okay, here we are. So I used equals, so I'm erasing, I'm only keeping the highest harmonic here. This needs to be plus equals, so that was the issue. While I'm at it, I'm going to set wavetable at ij equal to 0. So we want to make these non-null before we enter this. All right, so now we should have a functional product here. Down here, we have a lot of rich harmonics. You can tell by the pointed edges as we get higher. So if you listen when we get to the high range, it's really obvious that you can hear the click when it changes tables. Hear some aliasing, because as we approach that harmonic, some harmonics that were okay earlier in the octave are no longer okay and alias very obviously by the time we get there. So now we need to interpolate vertically as well as horizontally. So it's actually not too bad. This is called bilinear interpolation, since we're doing a linear interpolation in two directions. And essentially what that means is we have to interpolate the table behind us, the table ahead of us, and interpolate how far we are between those two tables. Okay, so we need to make a float low octave sample, a float high octave sample, and then our current sample will be the position between those two. So our low octave is what we already have. An interpolation of our current octave truncated with the phase +1, and then interpolated there. Our high octave will be very similar. Our current octave +1, so we're just checking the next octave with the same phase location. All right, one issue we'll have with this is that if our current octave is 9, we're adding 1. So that'll try to find our 10th, or our 11th rather, table, or the 10th index, which does not exist. So we need to write a simple way of making sure that doesn't happen. So there's something in C++ called fmin, float minimum. It'll find the minimum between this and 9. All right, so this function fmin will check these two things, our current octave +1 and 9, and give us back whichever one is lower. So it's a really easy way to make sure we don't go above 9. So we'll add this over here as well, fmin, current octave +1, reference that to 9. Whichever one is lower will come out. And then we still need to truncate that, because this is floatman, this returns a float, we still need an integer. Okay, so this has gotten very large, but you can break apart each part. So this is our wavetable, which table we're at. Alright, so this is which table we're at. This is how far we are into it. This is which table we're at. This is how far we are into it. And this is our interpolated value. So these are two different linear interpolations we have to use. And now we have to do one final interpolation. So this will be interpolating between our lowest octave and our highest octave. So our current sample equals linear interp of our low octave and our high octave. And we need to know how far we are between those two octaves. Unfortunately, our current octave is a float. So current octave already has that information built in. And my linear interp algorithm looks at that floating point number. So we could modulate this, or do an F mod, a current octave, and then 1.0. And that's what I would do originally, but I happen to know that my algorithm already makes sure that this does that. So we don't need that here. But say we had 4.3, this will just give us 0.3. If we had 6.8, it would give us 0.8. So we know how far we are between. But that happens inside of the linear interp to begin with. Okay, so now we should hear no stair stepping between the two. Okay, great. So let's go ahead and I'm going to, as the frequency changes, let's see, where's the best place? We'll do it here. Let's do a bitmap string, I think it's called. Yeah, I'll draw a bitmap string. We'll need a string, so of to string. We'll convert our frequency to a string. So a frequency dot current value. And we'll put that in the X, Y location here. So this will post our frequency, and we can do a quick test. So in this, our lowest viable frequency we said was 20 hertz, and I'd like to point out what happens if we go lower. So here we're a little lower, but if you go a little too far, you start to hear some high frequencies. So we don't have enough harmonics in this low of a frequency to accurately represent a square wave. So the reason you hear this ringing is there's not phase cancellation of the higher frequencies pushing those out. So it doesn't necessarily sound bad, it's just not representing a square wave, what a square wave would sound that low. So this has some limitations. I mean, if this isn't a problem, just leave it, or just cancel and don't let users go past 20. Or you could take this as many octaves low as you can. You can make it go to 10 hertz, 5 hertz, 2.5 hertz, etc. But it's not an issue. So, I mean, if somebody wants to use this as an LFO, they shouldn't be using a wavetable oscillator. And we can get into which oscillator would be appropriate for that later. But something that generates it is generally preferred. All right, so we have a square wave. Let's go ahead and add a triangle wave. So a couple new things we'll do is an enumeration. This will just be a handy name thing. Wave type. All right, and then we'll need, let's see, let's do a square, triangle, and sawtooth. All right, and we'll store integer type equal to, let's just do a square for now to make sure everything's fine. All right, so when I say square, it's actually replacing this with 0. Our type is equal to 0. So this is a way to make integers reflect what they're actually representing if you have a switch. So I have 3 different modes for this table, or I will when we're done. So we need a square mode, a triangle mode, and a sawtooth mode. And now we have an easy way to change that and make it logical. So a switch, we'll check our integer here, which will be type, and then make certain things happen. So if the case is a square, do what follows. Break. Case triangle, or 1. It's just doing text replacement there. Case sawtooth. Break. And it's good to have a default. If it doesn't find any of those to be true, do this. We'll just report it. Not a valid type. So this is a bit of error checking. Break. Okay, cool. So we need to put our logic to make a square table. condense it a bit. Here. So if we tell it to make a square table when we start, it'll run this code. If we tell it to make a triangle, well, we'll get there in a second. Let's make sure we haven't broken it first. Great. All right, so the rules for constructing a triangle table, or triangle wave with sine waves with additive synthesis is very similar. One thing we need to change, as a matter of fact, there's two things we need to change. Instead of taking the sine of theta, we take the cosine of theta. And then instead of taking 1 divided by our harmonic number, we take 1 divided by our harmonic number squared. So we're still taking every odd harmonic integer of the fundamental frequency. So if it were a 20 hertz tone, we'd take 20, 20 times 3, so 60, 20 times 5, it's 100, etc. All right, and this happens to make a triangle. So let's go ahead and take a look at our triangle wave. Let's change our type to triangle. Harmonics are a lot quieter, and that's because they dampen as they go exponentially. So aliasing isn't as much of a problem to begin with, but it's good to prevent it if you can. All right, and a more aggressive waveform is the Sawtooth. So these both had only odd harmonic multiples of the fundamental frequency. These Sawtooth has all harmonic multiples, so 1, 2, 3, 4, etc. So we'll still start on the first harmonic, which is the fundamental. But instead of increasing by 2 each time, we'll just increase by 1. All right, and to make this the correct direction, a Sawtooth can go up or go down. It's just a ramp. The correct direction is to do the polar opposite, 100 degrees out of phase, or flip polarity rather. Out of phase isn't technically correct. But this should start out the correct way. But note that if you're listening to a Sawtooth wave, it doesn't matter which direction it's pointing. Our ears are not sensitive to phase in this way. So bear that in mind. It can face either direction and sound the same. So it depends on your purpose. But let's go ahead and make sure our Sawtooth wave is correct. I have forgotten a very important part, and I should have done this earlier, but you know, it's too late now. We need to normalize it. Let's run this again. You'll note that I am mapping this waveform from -1 to 1 to the top. So if we had one sine wave, it fits perfectly in our screen. But if we add harmonics, our amplitude of the table is bigger than -1 to 1. And we need to make sure that doesn't happen. So after we make our waveform, we need to have a function to normalize. So normalize the wave tables. It would be neater to write this in a function, but let's just write it below here. All right. So we need to normalize every one of the 10, each octave, each table here. So for int I equals 0, I is less than 10, increment I. So each table, and to normalize, I haven't found someone else's reference how to do this. This is the way I've always done it though, and it seems to work fine. We could make sure we don't have any DC offset, but we know that we will not have DC offset because we're generating these ourselves. So we don't have to worry about DC offset. But to normalize, what we need to find is our largest value. So for every value in this table, for int j, while j is less than table size, increment j. All right, so we need to find our largest value. So let's set largest value equal to 0. And as we move through our wavetable, if our wavetable table at I, j is greater than our largest value. Our largest value then equals that value. Okay, so one issue is that negative numbers will never win this round, and we need to make sure it's not biased by polarity. So let's take the absolute value. And in C++, it's called f_abs because absolute value returns an integer. Float abs is returns a float. We need a float here. If it's greater than largest value, our largest value equals. All right, so what could have happened if we didn't do it here is that we could accidentally flip the entire table, which wouldn't be a huge deal again, but it would be kind of problematic when we're interpolating between tables. All right, so after we find our largest value, we need to go through this entire table again. Let's erase this middle bit. We'll go through the entire table again. But first, let's find out our scalar value. Float scalar value equals our 1 divided by double largest value. Might as well. Oh, this is going to be a float. Let's make these floats. I'm bad about doing that. All right, so now we have our scalar value. Now we need to take each element of that array, or of this buffer, times that value. So for every value, wavetable at I, j, times equals scalar value. All right, so let me comment this up. First, we need to find the largest value, ignoring whether it's negative or positive. Calculate the adjustment value. Multiply each member of that table by the adjustment. Okay, and then we do this all 10 times, so 1 for each table. All right, so that was fast. I didn't mean to go through that so fast, but that's how you normalize a wavetable. And maybe in a later tutorial, we can talk about DC offset and ways to optimize this. Let's go ahead and try this again. And it's fun to watch how this happens, how a sine wave, you add some harmonics, eventually we have a pretty tight waveform. Let's try the square and make sure these all normalize the same way. Okay, great. So you can see this is normalized to the screen as well. Okay, great. So this is a very efficient way to produce these tones. I mean, imagine, let's just do a quick test. Where are we? So for our square wave, C out, all right, table, let's see, that would be I. All right, let's make this octave. Octave I has num harmonics. And now we'll see the real value of doing it like this. So our console will print out the number of harmonics for each table. Oh, something's very bad indeed. But let's see if it's still here. Huh. That's a new one to me. It's still going to tell us how many harmonics, but I put this in a bad spot. You can see that well, yeah, so I repeated this 2,048 times, so that was a mistake. But octave 0 has 1,001 harmonics, it looks like. So, right, so we can see that there are a ton of harmonics. So if we wanted to represent the same sound with additive synthesis alone, we would have to have 1,000 sine wave oscillators for our lowest octave. And you can see as we go up octaves, it's not as big of an issue, but it's kind of absurd, and it's not really a practical thing to do to have that many sine wave oscillators. Even if you use a sine wave table oscillator, that's still an insane amount. So the big advantage of this is you can have really rich harmonies or really rich harmonic content synthesized without being really computationally expensive. The limitations of this method is that we cannot control the duty cycle of this square wave at the moment, and we could not change the asymmetry of the triangle wave if we wanted to. So they're not modulable, but they are very efficient. This covers a lot of your needs for a basic oscillator. So if you have a synth that needs a square wave and you don't care if you can adjust the duty cycle, then that's fine. It'll work great. If you have a triangle that you don't care about adjusting the symmetry, then that's great. So it depends on your needs. We will, in a later tutorial, and cover a way of generating a low aliasing oscillator without while being able to adjust the symmetry. So you can't store the value, but that'll be another tutorial on that. Thank you for watching.